I think we're recording. Okay, so here's the readings for, I will put this in the chat here. I will also post it on Piazza. So here are the readings for this coming week. This is number 1. And this is number 2. And so these 2 papers are papers on in communication complexity. I'll post the notes hopefully pretty soon. I'm planning to do it tomorrow. So those will be lecture notes on communication complexity, and then I'll also record a lecture on the same topic. But that probably won't be posted until Wednesday. So the topic is communication complexity. The papers. So in communication complexity, I find everything is a little bit difficult. It's all the proofs are kind of messier than in query complexity. So the papers have a little bit of that feel as well. And so in terms of taking up these papers, I was hoping to only kind of read both of these papers kind of have a separation between quantum and classical algorithms. They say, oh, in this one variant of the model, there's a quantum communication protocol, basically a quantum algorithm, but there is no classical algorithm. And the quantum algorithm is usually reasonably simple. It's often the classical lower bound that's very tricky to prove. Or certainly that's the case for Klartag and Regev, one of the papers I linked. So I was hoping to just completely skip the proof of the classical lower bound, at least for now, and only have students read the kind of quantum upper bound for both of these papers to kind of narrow down what you need to look at. And so when you're presenting the papers, even if the papers look long, you're only responsible for kind of a small part of the paper. Right. So with that in mind, does anybody want to volunteer already for presenting next week? I know it's.
I would be down to present one of the 2 papers.
Okay. Sure. Let me write you down then. I'll be sure. Okay, and let's get another volunteer for the other paper.
So I would very much prefer not to.
Okay.
Just before you start picking randomly, I just want to say, like, I very much cannot do it next week.
Oh, not next week specifically. Sure. That's part of the reason we're trying to schedule these. Yeah. You know what? If people are still a little bit scared, we can do the presentation for this week first. Maybe get a little bit of understanding of what that entails. Hopefully it will seem a little bit less scary. Yeah. So I guess Yuming is Yuming here? Yuming is here. Are you ready to present now? I can't hear you, Yuming. I mean, it looks like you're unmuted, but I don't. Okay. Oh. Can you guys hear Yuming? For some reason, I can't hear anything.
I can't hear anything either.
Okay, yeah, Yuming, we see your screen, but we can't hear you. I don't know why. Maybe just mute and unmute again.
Let me try this.
Oh, now we can hear you.
Sure.
Okay, yeah, you're good now.
Great. Make myself here. Okay. Yeah. So I was chosen by Schlaf's quantum random number generator to be the first presenter. And the paper is quantum approximate counting simplified. The approximate counting is that given a list of n items, of which k are marked, your task is to estimate k within a multiplicative error of epsilon. Here, multiplicative error means your algorithm should output a number between k minus epsilon k and k plus epsilon k. And a query of the ith item simply returns whether the item is marked or not. It is known that the best possible classical algorithm requires n over epsilon square k queries. And in 2002, those 4 authors for some reason. Oh, can anyone still?
We can't see your screen anymore.
Yeah, sorry for that. Just give me a second. I will change a device. Okay, I hope you can see me now.
Okay.
And my screen, right? Okay. Sorry for that. Yeah. So these 4 authors gave a elaborate quantum query algorithm. Provides a quadratic speed up over the best possible classical algorithm, and this is the BHMT algorithm. And according to an early paper, this is actually an optimal quantum query algorithm. And as we can see, the approximate counting problem looks like database search, but not the same. And indeed, the BHMT algorithm uses the QFT as a K ingredient. Here, QFT stands for quantum Fourier transform, not for quantum field theory. So the BHMT algorithm is a sort of hybrid of Grover's algorithm and Shor's algorithm. And as we all know, well, actually, I don't know, but I will pretend I know, the quantum Fourier transform is very expensive in a real-world implement of quantum computing. So in this paper, which I will refer as AR20, the algorithm is QFT-free. It is based entirely on Grover's interactions. And it is, of course, optimal. It still provides a quadratic speed up over the best possible classical algorithm. And as the title suggests, the algorithm is extremely simple, and it can be generalized to amplitude estimation. Well, it is nearly trivial to generalize approximate counting algorithm to an amplitude estimation algorithm. So that's one reason why we are interested in approximate counting problem. And the formal statement of the algorithm of the theorem is here. So given approximate counting problem where k out of n items are marked, and given a constant epsilon, a constant delta, well, this epsilon is related to the error, and delta is related to the success probability. The algorithm outputs an estimate k within a multiplicative arrow epsilon, and the algorithm uses 1 over epsilon square root of n over k log 1 over delta queries and log n qubits, and the success probability is at least 1 minus delta. And I will present a sketchy idea of how this algorithm works. So first, let's consider a classical problem. Given a biased coin, which is heads with probability p, your task is to estimate p. This task is extremely easy. So first, you just toss the coin 2 to the t times, well, t ranging from 0 to 1 to 2, until you observe heads at least once. And this gives a rough guess for the probability p. And of course, you can toss coin more times. This will give you a better approximation on p. And the essential component in this paper is the Grover coin. So let's first recap the protocol of Grover algorithms. So suppose given k out of n items, k out of n items are marked, and the initial state psi phi 0 is basically the superposition over all indices, and we can view this initial state as a vector in a two-dimensional space spanned by x and y. Well, x is simply the superposition over all unmarked indices, and y is the superposition over all marked indices. And your psi 0 is basically cosine theta x plus sine theta y. Here, theta is it's just square root of k over n. And each time you query the state, it gives you a Grove rotation, which is basically a rotation by 2 theta. So after k queries, the state becomes cosine 2k plus 1 theta x plus sine 2k plus 1 theta y. And measuring this phi k is basically a biased coin. Why? Because you can simply view y as the heads and x to be the tails. So when you measure the state, it will give heads with probability sine square 2 plus k theta. So in conclusion, for any odd number R, well, here I is basically 2k plus 1. Grove's algorithm will prepare a biased coin, which is heads with probability sign square r theta by making OR queries. Well, here OR is roughly R over 2. And the trick here is you use this coin repeatedly, and each time you adaptively vary the value of R, and this will give you this will help you zero in on the correct value of theta. And since theta is basically arcsine square root of k over n, this will give you k. So for example, if you have a good sense of what k can make this probability close to 1, then you have a good approximation to theta. And k is just theta square, then you will have a good approximation for k. So that's the sketchy ideas of this algorithm. So I guess that's all I want to talk in my short presentation.
All right. Yeah, great. That was perfect. How do you do this? Okay. Well, anyway, thanks, Yiming. Yeah, so that was about 10 minutes, which is exactly you know what we usually budget. And yeah, so as Yiming was saying, so this paper, you know, basically it's a reproof of an old result. You know, and the reproof only works by doing Grover search instead of, you know, the old proof, which used or the old algorithm used a combination of Grover search and Shor's algorithm, basically, where you know, basically the old algorithm considers, of course, Grover search. If you keep rotating, if you keep doing this rotation in Grover search, then eventually you loop around and you rotate the full circle. And so you can, of course, ask. You have this rotation which is periodic. Then you can ask, what is this period? And you can just basically plug this into Shor's algorithm that will give you the period. And if you know the period, then you will know theta, right? So you will know by how much you're rotating. So the old algorithm basically does that. The new algorithm says, okay, that's really overkill. You never really needed, you know, Shor's algorithm. You can tell what the period is just by seeing how much you need to rotate before you see a 1 when you measure. So just try different amounts of rotation until you see a 1 when you measure. And then that should tell you at least roughly by how much you need to rotate. And then you can zoom in by basically just repeating several times to amplify this probability. Yeah, and anybody else have any thoughts on this paper? Or any questions for Ewing?
I don't know if you know the answer to this, but in the introduction, they talk about how the speed of the racers needs to be about close to 1, the ratio of the speeds of the two queries. How does why does that need to be the case?
Which part?
Hold on, let me try to find it. It's near the end of the first section. Oh, okay. On page 3, near the end. This end of this last paragraph that's there. Yeah, right. With the 2 and the other 2.
Here?
Sorry, I can't see your mouse. Go up a little. Yeah, so the footnote at the bottom, is actually the exact thing.
Right.
Oh, actually, I have no idea how this works. I guess we have to read into details of the algorithm.
Yeah,
So,
that's right.
so I mean, yeah. One difference here between Shor and Grover is for this amplitude estimation is that they are estimating the angle even when the angle is far from zero. So for Grover search, you just generally want to know like rough. You want to find a 1, so you basically want the angle to get large eventually. And here, so they're sort of they want to estimate an angle even when the angle is already large, and so to do that, then you think, okay, so suppose I had a gap between two angles. So suppose I'm trying to estimate this angle, but I don't know exactly where it is. So I want such that if the angle was slightly this way or slightly this way, like I could tell those apart. Like I could tell this if there was a small gap between the two angles, I could tell it apart. So that's the theta min and theta max. And the idea is if you sort of rotate enough, every time you're rotating, in case 1 you're rotating by a larger angle than by case 2. So in case 1 your speed is like faster rotating around than case 2. Eventually, if you compare the two and go around enough times, then the ratio between the two angles will start being a constant. So even if it started out small, then eventually when you repeat this, then the ratio will be a constant.
Okay, yeah, that clarifies it enough for me.
Yeah, so I think that's partly what's going on there. Is the part of the trick for this paper is basically what you do to estimate a larger angle, but you want a tight estimation of what it is. So you don't just want to measure a 1. So you don't want to just rotate it until it's kind of high. You want to like estimate exactly what it was. Mm-hmm. And so to do that, then you need to kind of distinguish the case where the angle was off in the high side and off in the low side. And that's, I think, going to be their theta min and theta max, or I mean, something like that.
Yeah, I think like in the paragraph above, it says that you basically want to what is that? Do a binary search to keep shrinking theta min and theta max until you get close to theta.
Yeah, I see.
Yeah.
And also, I would say something that helps me think about it is, I think the key part is when they say that you need that the ratios not be, be far from any rational with a tiny denominator, because you essentially need you're applying an integer number of rotations, and therefore you need for it to create a bunch of points which are somewhat dense in the unit circle or like around the circumference of it. So that eventually you do get close to this 90-degree angle between the two, so that both of the subspaces are orthogonal. And the saying it's close to 1 is just an easy way of ensuring that it's not like this rational.
Oh, okay. Yep, because 4/3 would be, or
well, so what they mean is that if it's sufficiently close to 1, then it's sufficiently far from any rational with a small denominator. And I think that's really all they want to ensure.
Okay. Yeah.
Okay. Any other comments on this paper or on the presentation? All right. Maybe we can get back to seeking a volunteer for next week in this case. Okay. So as you can see, I'm only looking for kind of a short 10-minute thing. I guess Yuming had a bit of a presentation prepared. In general, you can also just share your screen and literally share the paper and scroll through it. Especially if you can figure out kind of a highlighting app where you can kind of highlight things that you were talking about because people can't usually see your cursor, then that would be great. But you know, you don't actually need to prepare even this kind of 1-page or 2-page slide that you did. So even that is it's okay not to do if you just want to kind of share a screenshot, you know, the screen and open the PDF and scroll through it. Yeah. Any takers?
I'll say I don't feel too comfortable with the communication complexity, but
Okay.
I'll happily take it if no one else is willing to.
All right. So, all right. Thanks, Andrew. So, okay. So let's go with you and Abhishek for this coming week. So again, just a reminder, I guess the number of people in the meeting increased, so I'll just repeat what I said at the beginning. So for the readings this week, which I will post shortly on Piazza, and I've put in the chat. So they're in communication complexity, and I mostly want you to read about the quantum protocols, the upper bounds on quantum communication complexity, and not and maybe the background for what's problem. It's, you know, just the introduction sort of what the authors are trying to do. And you are not responsible for the classical lower bound, especially in Klartag and Regev, where it's kind of tricky. But you know, in both, I would say. So basically, don't worry about the proof that classical algorithms cannot succeed. That proof is often tricky. Yeah, great. So we have 2 volunteers next week. After that, hopefully we will know kind of the final number of people in the class, and we can start like start scheduling how many slots of presentation we need. I want everybody to present twice, hopefully. And so we may need to increase the number of presentation to 3 in some weeks. So yeah, we'll see about that once we have the final tally. I guess deadline happens. You know, but we should already have a pretty good idea soon, I guess. Hopefully people are making up their minds. So, but it looks like we may need some weeks with 3, so we might try that for the week after next. Next week is just the 2 that I posted and the 2 volunteers. So thanks to Andrew and Abhishek again. Okay, so any other feedback on the notes? So so I wrote up like this, I guess roughly 10 pages probably, of notes about kind of somewhat standard quantum algorithms, but how you would formalize them in query complexity. I kind of expect that for at least some of you have seen this already, so I don't know everybody's quantum background. So I realize that some of this should already be familiar. Yeah, anybody want to comment on kind of did you find it easy, or you know, was it already covered in another course? So I mean, last week you told me that quantum amplitude estimation was not covered or nobody has seen it before.
So
yeah.
Andrew, Randy, and I took quantum algorithms last summer, and so it covered basics of lower bounds and these algorithms and stuff. But I think no one else here has. So for everyone else, this stuff is newer.
Okay, well, I mean, there's maybe other courses that cover it. Who was that? Was that with?
That was with David Gossett.
Oh, David,
and what's his name? Richard Cleve doesn't cover this stuff in much depth in
I see.
710. Yeah.
I see. So yeah, so I see. So David Gossett, right? So David Gossett, I know covers a bunch of this in his course. Yeah, then Richard Cleve and John Watrous sometimes teach courses on quantum computing, but I guess John's been teaching his quantum info lately, which might not cover.
Yeah, he hasn't covered this sort of stuff in a while, at least.
Okay, fine.
I don't know about Cleve. Yeah.
All right, fair enough. Yeah, thanks. Well, in any case, if so again, I kind of expected this to be familiar to some people, but I also expect it to be new to other people. So if this is new to you, then then don't feel bad or feel like everybody knows this already. The secret is that you don't actually need to know quantum algorithms or most of quantum algorithm research. So a lot of quantum algorithms in practice, and by in practice I mean in papers published, in the last 5 years or so, involve calling these other algorithms as subroutines and basically only doing classical overhead on top of them. So this is just like the vast majority of stuff. It looks like that. So we will study in this course some exceptions. We will study quantum walks and things like that because the exceptions are more interesting. But when somebody tells you that, oh, they have a quantum algorithm for, what was it? Recently it was gradient descent or something, or something. Anyway,
Yeah.
it means that they're doing Grover search. So this is what everybody means when they say they have a new quantum algorithm for something, more or less. Yeah. So you don't really need to know how they work. You just sort of need to know their existence so that you can call them as subroutines whenever necessary. And also we will hopefully cover some lower bound techniques in terms of to see why some of these algorithms are tight, especially Grover search. For this coming week, though, we're going to cover communication complexity. So this is going to be kind of another kind of intro to kind of a week where the notes will have a bunch of definitions and so in many ways, quantum communication complexity is sort of just a richer or kind of more difficult setting than quantum query complexity, but it's sort of similar in many ways in that, so kind of a lot of say quantum query algorithms can immediately be converted into a quantum communication protocol for some related task. So we'll talk about it a bit more next week. But so for example, Grover search for solving the OR function in query complexity, it becomes basically an algorithm for solving disjointness in communication complexity. It's a function that will be in the notes. So and the protocol for that is almost identical. So nothing too much difficult is going there. And that's the case for many types of quantum communication protocols, is that they're secretly just query protocols, but not all of them. And the two readings that I assigned that are currently in the chat are examples of exceptions where they're quantum communication protocols. They solve a task using quantum communication, but they don't really look like query algorithms. They don't really look like they're just doing directly doing Shor's algorithm or something, or Grover search. They're really kind of an extra new quantum protocol to some extent, or they have at least some amount of difference from just the query algorithms. So and even in communication complexity, the story is that this doesn't happen too often. So there's a few of these kind of the things that are their own quantum communication protocol. Most quantum communication protocols are basically quantum query algorithms, just in a different setting. And again, most of the quantum query algorithms are basically just classical algorithms on top of Shor and Grover. So you just combine Shor and Grover in some combination, and you get a what you can call a new quantum algorithm. So yeah, sort of that's the case in communication complexity as well to some extent. Right. So of course we focus specifically on the exceptions. So on algorithms that feel like they're doing something new. Right. Any other comments on this week though? I guess we should probably talk about communication complexity more next week. So I mean, in the beginning of the notes, I put this kind of equivalence between two formulations of query complexity, or I guess the querying in phase, like phase queries and regular queries. Have people seen that before? That's
Yeah.
yeah.
Or
Okay.
I don't know about other people.
Okay. Yeah, I mean, I guess it's somewhat standard if you study query complexity. I just trying to get a sense of people's backgrounds. I kind of, I was assuming that many courses wouldn't bother teaching about this because.
So at least what's it called? Like the phase kickback or phase querying is oftentimes covered, at least in like Richard Cleave's course or the first quantum computing course.
Okay.
But I don't know about other courses. Yeah. But I think that's a common tool when was it Deutsche Josa is discussed? Is that the one that it's most common in? I think so.
I guess, yeah. Okay. Yeah, so I mean, yeah, basically what happens in query complexity when people actually want to discuss a new query algorithm that doesn't just call SORG or something, then they specify, then they say, oh, now we query in phase, or they say, now, I guess the other query doesn't really have a name, which is a bit annoying. They either kind of make this normal query, or they say, now we query in phase, and they assume that everybody knows what that means. Right. Interestingly, I guess in Shor's algorithm, you don't want to query in phase, but in, say, Bernstein-Rezerani or something, you do want to query in phase. So it's not like you always use one or the other.
That's just a matter of clarity, right?
Well, yeah, you can always convert between the two by doing another basically Hadamard on your.
Okay, just wanted to make sure. It sounded like you were saying like using phase and Shores would ruin it. Yeah.
Oh no! It will make you have to do yet another Hadamard or whatever, and it would be yet more messy notation. So Shores are already complicated enough actually in terms of the messiness of the notation.
Yep.
Yeah. So right. So no. It's only it doesn't change the model. It doesn't change quantum query complexity. So you can always translate the algorithm into one or the other model if you wanted to. But we're just trying to save on the number of times we have to do this Hadamard transformation and get confused about what happens. So yeah, this is, I guess, the only difference between the two is kind of this Hadamard on the query output register. Yeah. Right. Okay, so again, I'll just to repeat what I said at the beginning. So for next week, the plan is we'll cover communication complexity. We will. So I'll post the notes probably tomorrow, and then the video. I guess I might not be done with it tomorrow, but I'll have a video as well, probably on Wednesday. Hopefully, it will be a higher quality video than last time, but I guess I can't completely guarantee it. So I'm trying to improve, but we'll see how it goes. Yeah. Do Abhishek and Andrew, did you guys have preferences for the time of the meeting next week, or the day? It doesn't have to be on Monday.
No, this should work for me.
Okay. Andrew?
Yeah, this works as well. So.
Oh, great. Okay. Well, everybody likes this time. All right. So I only got one student complaining privately about this time slot, but only for this week. He's actually said that in the future it should be fine. So I think maybe we just keep the slot as much as possible if it works for everybody. Okay, so great. So we will do it again on Monday 4:30, and of course I'll put that on Piazza for the people who couldn't make it this week, which potentially is only one person actually. Right, okay, so I guess that covers that. Any other questions about this week's content or anything? All right, fine. I'll talk a bit more, just a little bit more about quantum amplitude estimation in that case. So I mean, I guess the paper really focuses on this approximate counting problem. They really want to, take an n-bit string and just estimate the number of ones, like the Hamming weight of the string. That's what they want to do. What I'm usually more interested in doing is not that. It's, basically amplifying quantum algorithms. So if you have a quantum algorithm that makes a small bias, like a bias gamma, you'd like to amplify it into an algorithm that makes constant bias. And so the notes talks a little bit about that. And, basically, usually classically, you would pay 1 over gamma squared. So classically, if you had a coin, that the probability of heads is, a half plus epsilon, a half plus a little bit. And you basically want to know that little bit. You basically want to know whether it's above a half or below a half. Okay, so it's a half plus epsilon, this coin, but you don't know if epsilon is positive or negative. So it's either half plus epsilon or half minus epsilon, I suppose. Okay, so and kind of you want to know this two bounded error. So you right now, if you just flip one coin and give it as output, then let's say you say positive if the coin comes up heads and negative if the coin comes up tail. That's your guess on the sign of epsilon. If you do that, then your error is very large. Your error is close to a half, right? You get it wrong roughly half the time, right? A half minus epsilon, I guess, of the time or whatever. Okay, but you could flip the coin many times and kind of try to ascertain what the probability of heads of this coin is. And the number of times you have to flip before you have a constant error estimate of this sign of epsilon, whether it's a plus epsilon or a minus epsilon, the number of times you have to flip is 1 over epsilon squared, roughly. Okay, so it's quite a lot. Like if it's for example, there's this gap majority problem. I guess I probably mentioned it in the notes. So, your input string is either of Hamming weight n over 2 plus root n or n over 2 minus root n, and you want to know which. So by picking a bit at random, you can get this biased coin situation. By picking a bit at random, you get a coin that comes up heads with probability a half plus 1 over root n or half minus 1 over root n. And kind of you want to know the sign, like is it a half plus or half minus? You want to know that sign there. And it turns out that you really need n queries. You need to read basically all the bits before you can solve this problem classically. Okay, but kind of magically, you can do it faster quantumly. You can take any quantum algorithm which achieves a small bias, which succeeds either with probability a half plus epsilon or half minus, either up with one probability half plus epsilon or half minus epsilon, depending on the input. And then you can determine amplify that quantum algorithm to constant error, basically determine the sign of epsilon there, using 1 over epsilon repetitions. And that requires basically using your quantum algorithm to do kind of a Grover rotation across your like basically doing a Grover-like thing. So it requires uncomputing your quantum algorithm. You're going to have to turn this quantum algorithm, your quantum algorithm produces a final state, I guess, that if you measure it, comes up heads with probability a half plus epsilon or a half minus epsilon. This quantum state is not enough. So if you just ask for many copies of this quantum state, that's not good enough. The quantum algorithm needs more to amplify. To amplify, you need to uncompute this state. You need to kind of be able to undo this and work backwards. Apply the inverse of the algorithm in order to do a kind of a flip across the state, to do a rotation across the state, instead of just having many copies of the state. And that allows you to do a Grover-like algorithm. And then you can, basically the same algorithm as this approximate counting, lets you estimate the probability of success. And if you estimate it to error less than epsilon, then you know whether it was a half plus epsilon or a half minus epsilon. Okay, so I mean, I guess that's the main takeaway. So if you kind of didn't follow this, didn't understand this paper, or didn't follow much of this week's notes, I guess the main takeaway from this week is that quantum algorithms can amplify errors faster than classical ones, especially in this context where you start with very large error, you start with error close to a half, and you want to get to constant error. Then quantum algorithms get you a quadratic speed up there. So, if one way of designing quantum algorithms will, of course, be first design a quantum algorithm that has a small bias of success. It has large error. Then apply this black box amplification on it. So for gap majority, you immediately get a root n query quantum algorithm, which turns out to be tight. And yet, if you just tried to use Grover search as black box or something, you would not be able to get a root n quantum algorithm for that gap majority function. So this amplitude estimation is is a neat tool that it helps in many cases. All right. Any other questions or comments on this week? Okay, so if not, I think we will stop here. I will post. So as usual, I will post the video that's being recorded currently. This video for this class will be posted on YouTube. I'll also, as I said, I'll try to post the notes for this week on communication complexity tomorrow, and the video for this week on Wednesday. That's my planned timeline. So hopefully I'll stick to that. And then we will meet again on Monday to take up the 2 readings, and I'll put them on Piazza. They're currently in chat, but I'll put them on Piazza soon. All right. So I guess I'll see you all next week.